I'm building a flying boat. I've never built a fixed-wing aircraft before and I'm not trained in aviation manufacture or design. But hey, did that stop me last time? I must say, thanks for all the support on the last video with regard to uploading content on the flying boat build. It seems the majority of viewers are interested, which is great, and for those of you just like helicopters, rest assured there'll be more content to come on this. Here is what I've been up to. The tail is built with elevator and rudder now hinged. I'm quite pleased with it, and in particular the design of a few machine parts to hold it together, which I'll show in more detail later. To progress to the next stage, I need to know where the tail should go. And before you all shout out at the back, there is more to it than that. I need to know how far back from the CG of the aircraft and how high off the water it needs to be. The waterline with the boat on its current wheels is 22 inches from the floor. The tail is currently suspended just above that, which means it needs to go up. The white barrel and block of wood simulate the water level. We are now about 7.5 inches above the water, but is that enough, I ask? The top of the vertical stabilizer is 97 inches above the ground, and this will be even higher when the boat is on the trailer, which means when on the trailer I probably won't be able to get it through my workshop door. A minor consideration perhaps, because there are more important factors to consider. As we know, when a fixed-wing aircraft takes off, the angle of attack is increased by pitching the nose up. This allows the aircraft to leave the ground at a lower speed. I'm wondering what angle of pitch up I need to allow for because I need to avoid the tail dragging in the water. A quick Google suggests that pitch up on typical aircraft would be between 5 and 15 degrees. If I went for a distance of 3.7 meters from the center of gravity to the end of the vertical stabilizer, a 15-degree pitch up would need 991 millimeters of clearance to the water. I'm currently at 250 millimeters and the tail already seems high. If I went for 5 degrees, then that would be much more achievable. This is what 7 degrees of tail clearance looks like. And 8 degrees. I think 8 degrees would be the highest I would dare consider, as I want the tail to receive air from the prop at 0 speed taxiing. Ideally, the prop would be the same height as the tail, and at the moment it's slightly above that. I'm trying to figure out how best to design the tail structure. I'm a bit limited with how the tail can be mounted because of the prop getting in the way, but I can mount bars below the waterline. When the boat is moving forward, they won't be in the water causing drag. Before going further, I'm wondering how much pitch up is actually achievable on a flying boat. It's not like an aircraft with wheels which can easily tilt back on the main gear. A boat is going to require much more force to achieve such a pitch change, particularly at speed. A quick message from James Greenberger explained what I'm missing here. Ground effect vehicles need to have a higher angle of incidence of the main wings so they can just take off when they get to the right speed. This means that I don't need 8 degrees of tail clearance and can bring it down a bit, but I will need to think about what angle of incidence the main wings need to be.
Have you done a calculation on calculated weight for what this is? I guess you can't do that because you're not quite sure how big
Not really.
everything's going to be.
Not really, but the way I've done it, so we've got 2 tubes of 1 inch and it's 1.6 millimeter wall. I can't remember what the imperial version is. But if I had a single bit of 75 mil round, which I could do instead of all this strengthening by triangulation. I think 2 75 mil tubes would be heavier than 4 at 1 inch for a start. So if you make these little crosses here, very small diameter, and make them as light as you can, I think the overall weight would be similar to that of 2 75 mil diameter tubes, except this would be way more rigid, much stronger doing it this way. The rather pathetic aqua rudder can now be removed because it won't be needed. This thing was vague, and that's being generous. I need to decide how best to attach the tail boom tubes. The wheels will be going, and the brackets, as it's unnecessary weight. I've decided on a stainless steel tube welded to a stainless steel plate, using the bolt holes that were there already on the left, and I reluctantly drilled some new ones on the right. Back to the tail now, and I've made some gusset strengtheners, and I quite like how I've done it. What I did was drill the holes on one in the mill and then use that as a pattern for punching the others. Punching holes is fast, neat, and doesn't require deburring. With all the holes accurately placed, no gusset labelling will be necessary if it has to come apart. I made a little press tool to bend the edges down around the tube. This is 2mm thick 6082T6 and is hard to bend, so it has to be pre-formed. I want to talk about the decision to go for a conventional tail configuration over other types, in particular the T-tail. You will see T-tails used on ground effect vehicles quite often, and I wondered if I should also go for a T-tail. There are a couple considerations here. With a T-tail, extra weight and structure may well be needed, as the rudder has a leverage arm to twist the tail boom. With a conventional tail, the rudder is mounted more central to the boom, so there is less of a leverage arm. This means it can be made slightly lighter. However, the downside to a conventional tail is the elevator is intersected by the rudder, which means it has to be wider to compensate for the reduction in area. As this flying machine needs to be transported to the beach by road, a narrower elevator would have been a benefit. As I chose a conventional tail, this means I'll have to remove the elevator for transport and reassemble at the beach. I took this negative aspect in favour of a potentially lighter design, but I'm not sure if it was the right decision. I have also read that tail surfaces should be high enough as to be out of ground effect. I can only surmise that a tail surface operating in and out of ground effect will be oscillating in efficiency, and that might increase pilot workload. I've given this little thought as I'm not sure how much of an issue it might actually be. Control surfaces I've read give more lift below one chord length above the ground and reduce drag up to one span. The elevator will never be below one chord above the water, so I don't think it's an important consideration, but please tell me if I'm way off here. I will soon have to consider what angle of incidence the horizontal stabilizer should be. On typical light aircraft, this would be around -2 degrees. It is negative because it needs to push downwards on the tail to counteract a slightly nose-heavy aircraft balance. Fixed-wing aircraft need to be slightly nose-heavy to be stable in flight. For a neutral position elevator, the incidence of the horizontal stabilizer needs to be set correctly. A neutral elevator is important for hands-off flying and, of course, reduced drag. These are some designs I was sent by a gentleman called Paul. He has a YouTube channel called Freezertron. Link in the description to his channel. I wish I had his computer drawing skills. They really help visualize what it could look like. Paul has a great technical mind and a very keen interest in aviation. Notice the ideas for alternative wing options. There are so many design options to consider. What would you choose? Please comment. Thanks go to Paul for sending these to me. Check out this animation he created.